So in this lecture, we are going to study the register allocation, which is one of the most important optimization in the design of a C compiler. But before that, I'd like to rephrase the homework 7, which is the last homework, the assembly generation. And yeah, I uploaded a test script, which is like this: cargo test examples assembly generation, and it will compile some IR code into the assembly using your assembly generation code, and it will check if the results are the same. The IR's execution results and the generated assembly's execution results should be the same. So for now, it doesn't contain all the test cases I'd intend to test using the test, but it will be updated soon. And also, in a few days, I'd like to upload the small grader, which I set in the GitHub issue tracker, that will evaluate only a part of your assembly generation and the IR generation code. So as usual, you can submit your homework to GG, and the submission link will be announced soon. And I'd like to give you a tip about this homework. And for this homework, I'm not measuring any performance. I mean, your generated assembly code can be hugely slow. It is very much okay. Don't try to optimize at all, because it will introduce a few complications that will be needed in the implementation, and I don't want you to do that in this homework. The sole purpose of this homework is writing a correct assembly generation. So the concrete tip here is that use only 2 or 3 CPU registers instead of many for operands and results. So if you are adding 2 numbers into and saving it to a register, just use a fixed register. For example, R1 plus R2 equals R3. So you are not required to allocate registers wisely for the purpose of this homework. So that is the topic of today's lecture, and that is the topic of the final project. So let me move on to the final project, which is a performance competition, which is due at the same day. And you're going to submit your entire compiler, and I will provide some benchmark programs, and these benchmark programs will be compiled and executed on this board, which is a Hi-Fi unleashed development board. And it can boot Linux, and it runs RISC-V. So this is the first Linux bootable RISC-V development board. Okay, that's good. And if any of the results are wrong, if you are miscompiling the IR, the input C program, then you are going to be disqualified. But don't worry too much about it. You can resubmit your compiler multiple times. So if some results are wrong, you can see that, and you can resubmit. So that will not be very much a problem. And furthermore, the performance I'd like to measure is the geometric average of the number of cycles among the student compilers, and Clang -01, which is mildly optimizing the input program. So for this final project, you can do whatever you want to do in order to reduce the number of cycles. So you can implement all the optimizations we learned so far, and all the optimizations we didn't learn so far. So you can do whatever you want to do. I don't care much about your actual implementation. I only care about the performance result. And if your compiler is better than, for example, Clang -01, and it is a very much high achievement, I think, so you are going to get the highest recommendation I can give you. And if your compiler is better than most of the students, then you get A+. So that is a guaranteed one for this final project. So if you're very confident about your compiler, you can just submit no homework at all. Still, you're going to get A+ if you are good at this final project. And I recently got this RISC-V development board from Semi5, and 2 days later, on Thursday, I'm going to host the Dr. CEO Jo Myung-hyun of Semi 5, who will give us a talk about this RISC-V architecture and the innovation it will bring to the design of hardware. Okay, so this is a brief introduction to project. So I hope you start implementing some optimizations on the compiler. And in today's talk, I'd like to introduce the most important optimization, that is register allocation. So this optimization is not individually evaluated. So I will not ask you to submit the register allocator code on its own because it will be the crucial part of the performance competition. So it will be used. You are probably wanting to implement this for doing good at the performance competition. So okay, in this section we are going to explain how to allocate registers to memory or how to allocate IR registers into CPU registers. So I'm going to start with a brief summary of the context, which is memory hierarchy. So as many of you already learned from previous courses like systems programming or operating systems or architectures, so there is a fundamental trade-off among storages, that is capacity or density versus or speed or throughput or latency. So there are a bunch of classes of storages, including CPU registers, DRAM, the emerging storage of persistent memory, like Intel Optane data center versions, and solid-state drives, and is it solid-state disk? Anyway, SSDs, hard disk drives, magnetic tapes, and other kinds of storage as well. So the reason why we have many kinds of storages is that there is a fundamental trade-off among multiple storages. So CPU registers are very fast. So usually in a single cycle you can access CPU registers. So it is in the digital circuit, it is the fastest possible register storage in the design of a CPU processor. But the problem is that it has a very short capacity, or it is very not dense basically. So you can only have tens of registers inside a CPU. So the reason is that in order to support a very high speed, the capacity should be somehow limited. So this trade-off goes on with other kinds of storages as well. DRAM has much higher capacity than registers, but unfortunately it has a very lower speed than registers. So the torque to the DRAM takes tens of cycles or hundreds of cycles instead of only one cycles. So in between the CPU register and DRAM, there is a cache, CPU caches, which has higher capacity than registers, but lower speed than registers. But yeah, and so on. So the persistent memory, solid-state disk, and hard disk drive or magnetic tape has higher capacity. Even a single hard disk drive is 20 terabytes these days, but it has much lower speed. So a typical hard drive has 250 megabyte per second throughput, which is much lower than DRAM, which usually have multiple hundreds of gigabyte per second. Okay, so there's a fundamental trade-off of storages: capacity versus speed. And as a side note, I'd like to give you the first key idea in the storage systems, which is even though there are fundamental trade-offs, we can beat the trade-off by mixing multiple kinds of storages in a single system. So the idea here is that So we can achieve high capacity and high speed at the same time by caching. The idea of caching is that we can place hot data in the high speed and low capacity storages and cold data in high capacity and low speed storages. Here, hot means then that we are going to use this data very frequently. And the cold data means that we are not going to use this data in a near future. So hot data is used frequently and cold data is used infrequently. And if we place hot data in the high-speed storage, and then for the most of the time, we can enjoy high speed of the high speed the storages. And at the same time, cold data, since cold data can be stored in high capacity storage, we can still enjoy the high capacity as a single system, as a whole system all the time. So we can achieve speed and capacity at the same time if we are wisely placing hot data in the high-speed storage and cold data in the high-capacity storage. So that is the key idea of caching. And the theme, this caching theme, is again used in the optimization of this register allocation. So register allocation is basically mapping IR registers into a CPU registers and DRAM. And it is necessary because IR has infinitely many registers. So in KCC and LLVM and GCC, you can have infinitely many possible IR registers because you can just write down instructions on and on and on. So it is not fixed. The number of the registers are not fixed. It can be grow arbitrarily. So the reason of this choice is that it will greatly ease the implementation and verification of optimizations. So in the optimization, you can freely add new registers because of the infinitely many registers. And in the IRGen, again, you can use any number of registers because there are infinitely many registers. So it will ease the implementation of this IRGen. So that's the reason why we have infinitely many registers in IR. But on the other hand, CPU has finitely many registers, like in RISC-V, ARM, x86, and all the other architectures have finitely many registers. It is obviously for implementability in the real-world silicon. Silicon has a finite capacity, and it cannot support infinitely many registers, obviously. So that's the reason why CPUs has finitely many registers. And we need to somehow resolve the discrepancy between the number of registers. So we need to place so many IR registers into so small number of CPU registers. So that is basically the job of register allocator. So in a naive implementation of assembly generation, you probably place all the IO registers into only a few CPU registers, ignoring very many registers. And it is also a possible allocation, but it is not wisely placing data into registers. So the idea, the motivation here, or the goal of this register allocation is placing wisely the IR registers into CPU registers, so to maximize the performance. So the key idea here is that, as we discussed in the previous slide about the storage hierarchy and the key idea of the storage, placing hot data and cold data wisely. So again, we should place hot IR registers into CPU registers and cold IR registers in a DRAM. So that is basically the key idea, or the high-level theme of this high-level goal of this optimization. And this kind of placement is called register allocation because we are allocating CPU registers into IR registers. And as I said, it is one of the most important paths in terms of performance of a compiler. So the reason why it is so important for performance is that the CPU registers are much more faster than the DRAM. So as a result, recognizing the IR registers and placing them to the CPU registers is really the key to the performance. So without wisely placing IR registers into CPU registers, all the IR optimizations we have done so far, including register promotion or GVN or dead code elimination, will not help a lot, because otherwise they will still go to the DRAM. It doesn't affect the performance of the generated code a lot, because we are still going to DRAM. It is going to ruin the performance. So in order to enjoy the benefit provided by the register promotion and GVN dead code elimination constant propagation optimizations, we really need to map them into CPU registers as the final step of the compilation. Okay, so before jumping into the algorithm's details, I'd like to share a few terminologies that is widely recognized as a standard term of this problem. So the first term we should learn is assignment, which is basically a mapping an IR register to a CPU register. So we are going to assign a CPU register to our IR register. So that is basically saying that we are mapping an IR register into the corresponding CPU register. And there is a notion of coalescing, which is mapping multiple IR registers to a single CPU register. So this is possible. The reason is that we can, if the IR registers are not overlapping their lifetimes, then in other words, if we statically know that two IR registers does not live together, so for example, the value of A is not needed in some area of the code, and value of B is not needed in the other part of the code, then this A and B can be using the same CPU register, because the two IR registers cannot coexist at the same time. So such mapping multiple IR registers into a single CPU register is called coalescing. And we are going to use this coalescing for many times, because many of the registers actually have very short lifetime. For example, temporary registers, that is holding the intermediate result of computation inside an IR, is only defined once and only used once. And this definition and use are very near. We are immediately using the defined temporary register. So if such temporary registers are so many, we want to place so many temporary registers into a single CPU register because there are so many, and they are not overlapping with each other because they have very short lifetimes. So that is the wisely coalescing multiple registers is therefore a key to a good performing register allocator. And another important concept inside this register allocation is a move, which is copying the content of a CPU register into another. And you are going to use this move if you're compiling finals. So finals are essentially moving data into another register, right? And in order to compile these finals, you probably need to copy the content of the CPU register into another if the two registers are two IR registers are mapped to different registers. But more importantly, this move is really necessary to pack hot data in the finite set of registers. So suppose that this blue are hot registers and hot data, and we probably need to use cold data in some structured way. For example, we'd like to use consecutive registers to hold the value, and blah blah. Then if that happens, we need to pack this hot data into a smaller subset of the set of the registers. So in order to do so, we need to pack and move the hot data from, for example, this hot data should be moved to this, so that we are having a consecutive data of hot ones, and we are having consecutive registers of the cold ones. So it is a little bit figurative, but this packing will be really needed when you are going to, if there's a complex control flows. So if two control flows join with some finals, then we need to somehow match the used registers of the used registers in the incoming edges, incoming blocks. So we need to somehow rename the registers so that regardless of whether the control flows from which previous block, or we can name them consistently. So this packing is basically figuratively meaning such a thing. So the details of this move and packing will be explained in a later slide. So this slide is a little bit at the higher level. So just at this point of time, just please memorize the fact that at some point of time, we want to move the content of a CPU register to another. So we are going to study this concept in more details in a later slide. Okay, and we are going to discuss the concept of a spill. The spill is basically moving the content of a CPU register into DRAM. And usually, we are going to move the CPU register into the call stack that is residing in the DRAM. So the spill happens when some hot data in the CPU registers are becoming cold at some point of time. So if this is the case, we are just going to kick the CPU register into the DRAM, moving the data out of the registers. On the other hand, when cold data becomes hot, we are going to do the exactly opposite, which is restoring or moving the content of DRAM, which is in the call stack, into a CPU register. So by moving data from CPU registers or DRAM to CPU registers or DRAM, we can have a spill, a restore, move, and other things as well in the toolset. I mean toolkit of a register allocator. Okay, so far so good. And yeah, let's move on to the key challenge of this register allocator. Okay, so we are going to use such a tools: move, spill, restore, assignment, coalescing. And the goal here is to resolving the discrepancy between the number of registers inside IR and CPS. And the key challenge here is that we need to decide which data is hot and which data is cold. And after deciding which data is hot, we can wisely map hot data into CPU registers and cold data into the DRAM. So the reason why it is a little bit difficult or it is challenging is that it is a kind of a global optimization problem. You cannot see the code or only a part of the code and deduce that some data is hot and some data is cold. So you need to see the entire function, entire IR function to deduce whether a register is hot in some air and another register is cold in some air. And you need to deduce this using by looking at in the entire function. So that's the reason why it is called a global optimization problem. And the metric we want to optimize is basically the cost of spill and restore, basically. So in the terminology slide here, we have move, spill, restore. But move is relatively cheap. It is only costing a single cycle. It is moving data into a register to another register. It's just only a single instruction, and usually it is a single cycle. But spill and restore are different. They are accessing the DRAM. It is either reading from or writing to the DRAM, which will cost tens of or hundreds of cycles, and it is really costing much. So usually we need to find a mapping that is minimizing the cost of spill and restore, and it is a kind of reverse thinking. And what is hot and what is cold, and that is in a good mapping that minimizes the cost of spill and restore. Those IO registers that are mapped to CPUs are hot, and those IO registers that are mapped to data, the DRAM is cold. So really, the cost of spill, the global cost of spill and restore for the entire function decides whether each register is hot or cold. So in order to solve this optimization problem, you really need to model the cost of spill and restore and find a good solution with a low cost of the spill and restore. And as a general strategy to attack this problem, usually one of the most widely used technique is static mapping. So this static mapping is usually employed by C compilers, and we are going to use this as well. So C compilers usually find a good mapping during compilation before executing the generated assembly at all. And we are somehow, in some heuristic, we are going to find a good mapping from CPUs to IR registers into CPU registers, and we are estimating the cost of spill and restore, and finding a good mapping that has small cost of spill and restore. And then we are going to translate IR into assembly according to the static mapping. So this is the strategy we are going to learn for the rest of the slides. And on the other hand, there is a technique called dynamic mapping. And this is usually employed by just-in-time compilers for JavaScript. So the just-in-time compiler is that if you're given a source program like JavaScript, then you are compiling and executing at the same time. So that is usually called just-in-time or JIT compilers. And here, you are going to find a good mapping during a program execution and generate assembly, then run and see again. And you can and by profiling the execution of a program, you can see that, oh, this mapping is actually not very good, and maybe this another mapping should be better for performance of a execution. If that happens, then the JIT compilers are usually switching to another mapping, finding another good mapping or better mapping, and translating the IR into assembly again using the new mapping during the execution, and replacing the binary. So the old binary is looking bad, and the new binary is expected to run better. So we are replacing at runtime. And it is happening on and on and on. We are replacing the assembly many times during the course of the execution. So this kind of technique is usually employed by JavaScript or Java or .NET and other managed languages. And this is a very interesting topic, and I'd like to discuss much more about this. But unfortunately, I know very little about this topic, and this course is so short. So I'd like to study this, and I would like to open a graduate course for compilers if I know better about this compilation. Okay, so we are going to focus on static mapping because we are building a C compiler. And for C compiler, we need to find a good mapping before execution and during the compilation. And the key observation for finding such a good mapping is that the mapping problem can be reduced to the graph coloring problem. And in other words, a good mapping corresponds to good graph coloring inside a graph, basically. So let me explain briefly about this graph coloring. So a graph coloring is that. So here's a graph, and you're going to give a number, or usually called color, to each vertex. But the rule here is that no edges should connect to vertices with the same color. So if there is an edge between A and B, for example, then A and B should have different colors. And the graph coloring problem is that finding a color mapping that satisfies the rule with the minimum number of colors. So for example, if a coloring is using colors 0, 1, 2, then it is using only 3 colors. And if another coloring is using colors 0, 1, 2, 3, 4, then it is using 5 colors. Then the coloring with 3 colors is much better than the coloring with the 5 colors. So such a problem is usually called graph coloring. And surprisingly, this graph coloring problem is very much related to the register allocation problem. So let me explain how to reduce this register mapping problem into the graph coloring problem. So the first step to do is let's construct what is called a conflict graph of IR registers. So conflict graph is that you first need to analyze each IR register's life range. So in an IR, each register has a definition point. So thanks to the static single assignment property, we know that a register is defined only once inside a function. And it can be used multiple times in the function. And the range from the definition point and all the use points are called a live range of an IR register. So the live range means that this register's value is meaningful during this live range. From the definition point to the use point, the value should somehow be stored somewhere because it will be used for some time in the future. But after all use points, the registers are no longer necessary to be remembered because it is no longer used at all. So if it is the case, then the register is not in the live range after all the use points are gone. So to summarize, live range is the range in which the value of the registers matters and the value of the registers are necessary in the future. And it is from definition point to the use point, basically. So the precise definition of this live range and the implementation details will be discussed in the later slides. So this slide's purpose is to deliver the general idea, key idea, or high-level idea of this register allocator problem. And okay, so for constructing this conflict graph, we first need to analyze each IR's registers, and we're going to map an IR to a vertex. So we are going to construct a conflict graph, and each vertex corresponds to an IR register, basically. And the key detail here is that we are drawing an edge between two vertices or two registers if their registers are overlapping in terms of the live ranges. So that means if two registers' values should be remembered at the same time, then the vertices should be drawn with an edge. Okay, so yeah, right. So that means that so as a result, an edge means that these two vertices or two IO registers should not be placed on the same CPU register because their values should be remembered at the same time. Okay, now maybe you can grasp the high-level idea of this reduction. So if in this graph, in this conflict graph, if you can find the coloring with less than or equal to the number of CPU registers, then we are very much okay. the color of an IR register corresponds to its mapping to CPU registers. So for example, if an IR register is mapped with the color 2, then you can use R2 for the CPU registers. And if a register is colored with a color 4, for example, then the corresponding CPU register should be R4. So if coloring is less than or equal to the number of CPU registers, then we are going to have a very good mapping from IR registers into CPU registers. And thanks to the property of this conflict graph, we know that no CPU register is needing to hold values of multiple IR registers at the same time. So we don't have conflict at all because each CPU register doesn't have a conflicting vertices or conflicting IR registers. So basically, that is the high-level agenda, high-level theme of this reduction to this graph coloring problem. But from time to time, we cannot find such a good graph coloring. If there are so many IR registers and they are overlapping with each other very much, then the coloring number should be much higher than the number of CPU registers. So if that happens, we need to somehow give up. We need to somehow give up an IR register, and we don't try to map an IR register into CPU registers. So that procedure is usually called spilling. So you're going to just pick one IR register, and you should determine that, oh, this should be placed in DRAM. We are not going to be able to place this into the CPU registers. So it should be stored in the DRAM, and it will be loaded only when it is necessary to do so. So by reducing the number of IR registers, basically, we can have a graph coloring with lower number of colors, thereby succeeding to allocate the registers into CPU registers. And the key challenge here is that we need to decide which IR registers to give up, and we need to decide it very wisely. Because if you're going to give up a very hot IR register, then it will be very detrimental to the performance of the generated code. And as a result, it should not be too hot. And at the same time, in the giving of the IR register should give us a considerable benefit in the graph coloring. So, for example, if it has many neighbors in the conflict graph, then it is expected to benefit for the graph coloring problem. So you need to choose such IR register. Okay, so far I explained the overall algorithm, and here is a summary. So the summary of register allocator algorithm is that you first draw conflict graph of IR registers using the notion of IR ranges, and color the graph. And if the coloring number is less than or equal to the number of CPU registers, then we are done. We can just map the colors to the IR registers. And otherwise, we find registers to give up, and then spill the register and begin again from the beginning. We draw the conflict graph of the spilled with the after splitting an IR register, and on and on and on, until we get a good graph coloring with less than or equal to the number of CPU registers. So that is basically the overall algorithm. But there are a few implementation details we need to discuss, or a few heuristics we need to discuss. So I briefly explained how to choose an IR register to spill wisely. So it should not be too hot, and it should not give us. It should give us some considerable benefit in the graph coloring. But it is a little bit hand waving, right? It doesn't give you a very precise metric, and finding such a precise metric and implementing the metric is really difficult undertaking. And this kind of undertaking is usually requiring a long line of research. So there are a lot of papers that is solely on this register allocator and how to pick a spill and blah blah blah. And honestly, the best answer I can give you for how to wisely choose an IR register to spill is I cross my fingers to you. Good luck finding a good register spilling strategy on yourself. And honestly, finding a better strategy will give you a slightly higher performance, but implementing this overall algorithm and choosing some some IR registers to spill instead of very wisely is the key step. So after implementing this overall algorithm, the spill strategy will going to benefit only a little. So the cost effectiveness of this finding a good spilling strategy is diminishing. So I'd like you to implement this overall algorithm, but for the first iteration, I'd like you not to think too much about this strategy because it will not give you much benefit. The second question is that, okay, so if we cannot color the graph, then we are splitting some IR registers. And is it the only possible measure? Is there any other ways to reduce the graph coloring number while not going to spill too much IR register? So there is a technique called a split, which is dividing a register into two or more, so that we can have two shorter life ranges instead of one long life range. It is widely known that splition is going to help you on the register allocator problem. But again, you probably don't need to implement split for the final project because the cost effectiveness of this measure is diminished. So again, implementing this overall algorithm is much more important than applying more optimizations on the spill strategy or other strategy like split or blah blah. So okay, so today we discussed a high level idea on high level what's going on about the register allocation, and I hope you can grasp the high level idea of these things. And we are going to study in more depth in the following lectures with code or examples. So I hope so. All I hope for this course, this lecture, is grasping the high level idea. And I'd like to make one comment about this this reduction to the graph coloring problem. And it is actually the paper that is proposing to reduce this graph mapping problem into graph coloring is about 30 years old, and it is published around 1990. And actually, it is one of my favorite, by far the most favorite papers in the literature of the programming languages and compilers. So, okay, I have two very favorite papers. One is this register allocation papers, and the other is the SSA, the static single assignment papers. So these two are very beautiful. I mean, they are capturing the key idea or the key problem of the compilation or program languages, and it is transforming into an implementable algorithm. And it is, it is very systematic. It is not ad hoc. It is not trial and error. It is systematically modeling the problem. And okay, there are some places where things are ad hoc, like wisely and blah blah, but it is trying to make as much components as possible less ad hoc. It is focusing some aspect of the algorithm that is ad hoc, and the other part of the algorithm is not ad hoc at all. So this kind of beautiful paper that is theoretically systematic and beautiful and practically important is the research I'd like to do in the future. And yeah, I'd like to make a comment that this register allocation algorithm and the graph coloring reduction is one of the one of the most beautiful concept in the study of program languages. Okay, this is the end of this lecture, and I hope you will study the follow-up videos on the same topic as well.